Hello, I'm Peter Joyce, Systems Integration Director for Sentinel Process Systems. I'm here to introduce you to a methodology for the chemist to unburden himself from the tedious, repetitive tasks that he normally engages in doing traditional batch chemistry. What we have here today is a robot that in essence takes care of all of the repetitive tasks and enables the chemist to do reactions at high temperatures, pressures, and systems that he would not normally encounter if he didn't have this system. The machine is a FlowSyn reaction system that is coupled to a fraction collector, and this enables the chemist to do these multiple reactions in an automated manner. Let me introduce you to the way the system works. The system we have here is a Uniqsis FlowSyn. This is the basic unit for the system. It's a robot, if you will, with various components that I'll get into in a few minutes. And this enables one to feed reactants under high pressure and temperature through these coils and chips. And in addition, the product from the reactions are collected over here in a fraction collector. Okay. So we'll start off here with just going through the various attributes. These are feeds at the top for the purposes of today. This is a demonstration. So I've got the feed dies passed through a set of high pressure pumps. These pumps are primed up here with syringes that actually pull the liquid actually through the pump to the high pressure side to get started so that the system is hydraulic before we start. You can also feed, instead of feeding from bottles, you can feed through these loops. The loops, in essence, provide for reagents that are extremely small volume or very, very high cost, and these are also set up on the high pressure side of the pumps. And we'll be going through that in a minute. We then go from the high pressure pumps to, this is a standard setup, is a mixing chip, 1.6 ml with high static mixers in it. And from the high static mixers, the fluid flows from there into into a flow coil. Flow coil here is 10 ml PFA, and it sits over this mandrel, and the mandrel in essence provides for high heat transfer. You can also get other coils of different volumes and sizes. This one is this one that's connected is 10 ml. This one is 20 ml. You can get them 2 ml up to 54 ml of all different materials of construction: Teflon, PFA, stainless steel, and Hastelloy, and they come prefabricated with fittings, so you can just take them out and put them in. It takes no more than 3 minutes in order to do that. Very, very compartmentalized and a modular system. There's a lot that's been thought through on this to make it easier for the researcher. The major attributes that can be set with this are the residence time inside the reactor, the volume ratio of reagents, the amount of volume of reagents that you use per reaction, plus the ratios of each, and also the temperature. And all those can be pre-programmed. And I'm going to go through with you how we get to that point. The other aspects of this is that there's other peripherals that go along with this system that I'm not going to show you today, for additional mandrel coils, refrigeration coils, a photochemistry reactor, and also one that measures UV under flow conditions. But the purposes of today is to actually show you the demonstration. So I'm going to start out by zeroing in on the main configuration screen. And there's 3 main screens here for this, and the configuration in essence tells you how you're set up. In essence, you tell the machine what you've got connected. In this case, we have a coil right here of HTPFE, but if that wasn't a coil, if it was something else, a chip, a reactor of a different type, we could put that in. But we have a coil here, so I'm going to put that back. And then the materials of construction, if it's not HTPFE, it could be PEEK, Hastelloy, or stainless steel, but it's HTPFE for this one. And the volume, we could change, if they have a different volume of coil, we could change that there as well. Now, as I said, the way this is configured is we have a chip, a mixing chip, that's feeding the coil. The reason we do that is we want the reagents to be mixed intimately through the static mixer, and in essence enable the fluids to flow through and be mixed before they go into the residence time of the coil. You can set this up in ways so that you don't have to go mixing chip to a coil. You could do several coils in sequence. You could have much larger mixing chips. These could be run under refrigeration. But again, for the purpose of the demonstration, this is what we have set up for today. We have a coil and a mixing chip set up. And then we tell the system what the dead volume is, how much volume is left over or that we've introduced. The way this system comes configured is the dead volume parameter is set to 0 because the manufacturers know what the connection volumes already are. There's no heat exchanger. There's a minimum pressure, of minus 0.5 bar, and that's so that if you go below that minimum, the system will shut down. The reason it's a slightly negative is in case there's a bubble in the system. You don't want the system to shut off. And in essence, by priming the pumps and getting them set up correctly and measuring the pressures, you'll know if you have a bubble in the system or not. You can also see it with the visual ones. An initial delay of 10 seconds. A maximum pressure in this set of conditions of 21 bar. And the reason for that is because we have a PFA coil, and that's the maximum pressure that it can take. However, if we had the stainless steel coil set in up here, we would in essence be able to run the pressure up to 200 bar if we wanted to. But this for purposes of today, that's a maximum setting. You can tell you the pressure unit, threshold is off, the equilibrium flow. The equilibrium flow is a flow rate that is used to, in between experiments, to bring the system up to temperature before the experiment starts. A wash volume in between experiments if you want to rinse out the machine, and of course, if you've got a really reagent that's really aggressive, you may want to increase that volume to 20, 30, 50 ml, whatever you want. And the loop volume is the volume set up for these loops. We're not using these loops today, but that's a parameter that you can set. So now we've configured the system. So in configuring the system, the system knows what's connected to it, and it knows how to carry on, if you will. The next screen is manual control. The manual control is in essence to allow you to, in essence, take a look and make sure that you set things up properly and that it's also running properly. And in essence, you can change the selection of the inlet valves to solvent or reagent. You can hear them click as I switch those. And also for the B pump as well, there's an A and a B pump here. So you'd use these switching valves here for priming the pumps with these syringes, and you're in essence pulling the liquid through to the high pressure side of the pump to make sure that it's hydraulically filled and you're ready to go. So then if I come all the way down, I've got I can set these pumps manually at whatever rate I want. So I'll set this up to 2 ml and do that again for this other pump up to 2 ml. Then come all the way down to run. So now I started the pumps up, and what you can see on the screen is that the pressure at each pump is measured. There's a pressure transducer behind each pump that's telling what the pressure is, and also a system pressure where we're actually measuring the pressure intermediate between the mixing chip and the coil. You could configure these tubing and piping to put this pressure measurement wherever you want in the flow system. So in essence, what this is telling us is at 2 ml per minute, I've got 20 bar at the pumps, and I've got 9 bar at the after the chip. So the pressure drop across the mixing chip is 11 bar, if that's of interest to you. And then from here, we have a back pressure regulator that is in essence imposing a pressure on the system. It's set at 7 bar. So the pressure drop across the open coil is only 2 bar. So in essence, it gives you a sense of how the system is operating and what to expect under manual conditions. And also, if you want to calibrate the pumps, you could take the flow offline, put it into a graduated cylinder, and in the course of going through the graduated cylinder, make sure that the pumps are delivering what you want to, which is another major attribute of these systems, that there's no measurement of the flow. You rely on the pumps to deliver the flow that they say they're delivering, and in essence, you do the measurements in between. And that, in essence, saves a lot of complexity and also cuts back on your ability to have to troubleshoot the system. So anyway, we've done configuration, manual control, so now we're going to set up an automated experiment. And in setting up the automated experiment, what we're doing is we're setting up the first one of 10. And in essence, by setting up the first one of 10, that table is filled out as though this one was copied 10 times. But again, what the researcher can do is change the temperature, residence time, or volumetric ratios, if you will, in order to determine the range of experiments that you want to do, especially if you're doing screening for a specific reaction. Fluids flow through the machine, and we'll show you that in a few minutes. What the fraction collector allows you to do is collect just a reaction product. The system makes times all the intermediate washings and equilibrium flows such that all of that is diverted to a waste receiver over here. and in essence, only the reaction product is collected. One of the major attributes of this is a pre- and post-collect volume. That pre- and post-collect volume allows the machine to collect either before the dispersion plug goes through, or either the heart cut of the dispersion plug or the entire plug. You would collect the entire plug if this reagent or materials were very expensive. You would collect only the heart cut if you wanted to see what the maximum concentration is. So these are attributes that you'd be able to set. So anyway, let's go through the rest of the automatic setup screen. So I'm feeding out of bottles, not out of loops. That would be the option here if we're feeding out of these intermediate loops that I said are on the high pressure side. The volume of reagents is here that I want to commit to each experiment. So what I'm going to do is I'm going to set these, again, these are arbitrary. I'm going to set this to 2 ml for each reagent. So the reason I'm doing that is because this coil is 10 ml and I'm committing 4 ml per reaction. So when we actually run this, we'll see that 4 ml go through the whole system and be collected by the fraction collector. But let me go through the rest of it. So this next attribute is the ratio of A to B. So this is the initial reaction. We're going to set that at 1 to 1. Then what we have is we set the temperature of the coil. So I'm going to set that above room temperature to 22. And this says column temperature. This is, says column temperature. It really means a mixing chip, because this is also a column holder besides a mixing chip holder. So if you had a packed column, this is where you would put it. And there's other attributes on the Uniqsis websites that would show you how a packed column could be put in there for hydrogenation reactions. This is the residence time attribute. So this is default is 10 minutes, but we don't want to spend 10 minutes doing that. So I'm going to set this back down to 5 minutes of residence time. And what you can see is I change that, the total flow rate changes proportionately. So the total flow rate will be 2 ml per minute. This is also for the first experiment with a ratio of 1 to 1. So each one of these pumps is going to be putting out 1 ml per minute to get a total flow rate of 2 ml per minute and a residence time of 5 minutes. You don't have to worry about that for the purposes of this experimentation, for this demonstration. What I'm saying is that the robot automatically calculates a lot of this for you. So if you've got an idea of the conditions that you want to run at, this is that pre-collect and post-collect volume that I talked about, where you're looking at the reaction plug and then determining whether or not you want to collect all of the or not of the dispersion. Final wash volume, an intermediate wash volume, and then go on from the next step is to set up the fraction collector, which is over here. Now there's many different types of fraction collectors that you can get, and the one that we have is called Optimize, collecting in an ampule for a small volume that'll go directly into your HPLC, or and then also collect on the same sample the rest of the volume that you've committed to the reaction. So that's the optimized fraction collector. So the attributes of this, there's a wait time for this is 1/10 of an ml, and here I like to set that at 2/10 of an ml. So the aliquot size is what's actually you're collecting to go for your analysis. So now I come down to the table view after that to set up the automated experiments. And this is really the heart of the machine. This is really what we want to get at in the fact that this is setting all the attributes for 10 reactions sequentially. So if you can see, the first line is the first experiment, and this is the baseline that we set up. And it's then, this baseline is now set up to be copied down for the next 9 experiments. But if I want to change the second experiment, let's say I don't want the ratio to be 1 to 1 anymore, I want it to be 1.3 to 1, I'm just picking that arbitrarily, and I want this temperature, instead of being 22, I want it to be 26, and the second temperature to be 26, and now the residence time, which was, this is now calculating the residence time of both the coil and the chip. This chip is 1.6 ml, so the total system volume is 11.6 ml, so that'd be the total residence time with those two volumes together. Let's say I want that residence time to be something different. I want it to be less than that, 3 minutes. So that's going to automatically change the flow rate. So with that, I can then go to the third experiment, change its ratio, and actually let's go in the other direction for this one. So I'm just arbitrarily changing the ratio, changing the temperature, set this up different temperatures just so you can see 32 degrees, and then a different residence time. So we'll change this down to, say, 2 minutes to get the flow really high for this third experiment. So as you can see, what the table does is a table provides you with a methodology for changing 3 experiments, and we can go through the rest of the table and line it up to be 10 experiments, and all 10 experiments are going to be collected in the fraction collector. Experiment through the multiple experiment table, and now we're going to actually run the machine. And in running the machine, you're going to see the fluids actually go through the mixing chip and the coil. So I'm going to come over here. So I hit the start button, and the start button brings up a configuration screen for the fraction collector to make sure that it's oriented correctly. And then I hit the last button is start experiments, and in essence this commits everything to the start. So the first thing that comes up is an equilibration screen. The equilibration screen in essence is showing the relative temperatures that are necessary, and we just heard it click, so the equilibration is done. So now the next screen that comes up is the status of this experiment. This screen is very important in that it tells you this is what's running all the time, and it's telling you where you're at. And where you're at is you're committing reagents to the reactor. This gray bar here says it's waiting for the reagents to reach the reactor, so it's the fluids are being drawn through the overall system to get to the mixing chip. The coil temperature is at 22 degrees C, the other coil is at 22 degrees C, and the pressure is 7.6 bar. This progression bar down here tells you that you're on your first experiment, 1 of 10, and there's 7.5 minutes to go for the first experiment. And that out of the 10 experiments, the way I've set up that table, it's going to take 1 hour and 16 minutes to go through all 10 experiments. So in essence, we've started. So the product now has reached the first chip, and you probably can't see that, but I can. There's a little bit of blue on the side and yellow on the left. This is food dye, so this is kindergarten chemistry, if you will. And we're mixing blue and yellow to make green. And very slowly, it's going to come out of these are the 2 feeds coming into the side of the mixing chip, and this is the outlet of the chip. And from the outlet of the chip, it's going to feed through this pressure transducer. We're measuring the system pressure here into the coil. And you're going to slowly see the green come up along the coil. In essence, about 1 minute or 2 minutes has elapsed. We've got the green mixing fluid going through the chip. And as you can see, the green is now starting to show up in this transparent coil. So what's happening here, we're waiting for the product to reach the collection valve. So in essence, what that means is the collection valve is still seeing solvent come through the rest of the coil because it was full. But up here you see that now the inlet and the A and the B have now switched from reagent to solvent. Why is that? The reason for that is we only committed 4 ml of fluid to this reaction, so now solvent is coming through and is rinsing out the rest of the fluid that's in the mixing chip, and that's going to now push everything through the overall system to the point where it gets to the fraction collector and we collect the reaction product. So as you can see, the chip is becoming less and less green as we rinse it with solvent, if you will, and the green band that's in the coil is now starting to move. It's going flowing from the bottom to the top, and it's moving through the coil at roughly at 2 ml per minute total flow, or 5 minutes of resonance time. Okay, so now what we're watching is showing the fluid go through the coil, and it's almost reached the top of the coil. It's still waiting for it to get to the collection valve. As you can see, the solvent has cleaned out entirely the mixing chip, and the 4 ml that we've got on the coil is still being slowly pushed out, and it's a little bit less green at the very bottom. That's the end of the dispersion plug. And now we've got the fraction collector just came to life, and now we're collecting our product inside of these sample vials. And so this has collected the aliquot of 0.2 of an ml, and now it's collecting the rest of it. So in essence, it's only the hard cut of the reaction product, and as the rest of the coil empties, it's now just going directly to the fraction collector. So in essence, that's the first experiment. And we've got 1 minute and 30 seconds left in that first experiment, and once that is over, then the system will reset based on the table that I put together at the very beginning and based on those conditions, and we'll get the second experiment to get started. And we'll show you that as well, getting that started. But I think you can see what's happening here is that it just goes over and over and over again and in essence does exactly what you want. And in an hour and 16 minutes, for the way I set the table up, you've got 10 experiments sitting in, your samples collected in a vial, and it's ready to be analyzed. So now we're running into the second experiment. We're equilibrating. The second one, the temperature was set up to 26 degrees C, so now the mixing chip heater is heating up, and also the coil is. Obviously this is at 26 degrees C, so it's not high temperature. One thing I should mention is there's also a cover that goes over this for safety. So now it's coming up to equilibrium, and when the temperature here gets to within 2 degrees C of the desired temperature, we're almost there yet, we'll go through a starting sequence. So we've got just a few more tenths of a degree to come up. So now we're within 2 degrees C of this new reaction temperature, and we get an auto start sequence. That's the beep that you hear saying, okay, get ready, we're going to start the second experiment. So there's a countdown for that. Temperatures are coming up just a little bit more because we set them at 26. And now we've started the second experiment. And this is the status, and you can see the fact that we're on number 2 out of 10, and with 3% of the way through that. This is a much faster flow rate, and it'll only take about 4.5 minutes. And we're waiting for the reagents to reach the reactor. That's what's showing here. So the fluids are still coming down through the feed lines to the reactor here. And the first reactor is the mixing chip. And now it's reached the chip, so it's starting to fill in the blue and yellow on these sides like we did before. And now what the status bar here tells you is it's waiting for everything to get to the collection valve, which means it's got to go all the way through the chip, all the way through the coil, and then over to the collection. So in essence, you have your second reaction started. I didn't do anything. I just let it go and just explained to you what was happening. Just want to get across to everyone that this has been thought through in detail from the chemist's perspective. So now just heard the clicks, and you can see the green is now starting to show up and strongly now in the mixing chip, and now it's coming out of the mixing chip and into the coil, and you can see the green starting to advance the coil just like we did before. Okay, so we're got 2.5 minutes left. As you can see, the valves are switched over again because the 4 ml have already been committed. So we've got solvent going through the mixing chip, and that's starting to clean out. And the green band with the 4 ml that I put in here is now starting to advance again through the coil. And the solvent is coming behind that, and that's pushing out the last volume, if you will. And as this advances all the way through the coil, as you can see it, and it'll go over to the fraction collector. Obviously, if we have these PFA coils that are transparent. This is for the purpose of the demonstration. If you had a stainless steel coil, you would not be able to obviously to see what's happening. But we recommend just getting the PFA coil and setting up this demonstration with food dye and IPA, just to get a sense of how the system operates, so that you know how the parameters are interacting with each other. It'll take you not more than a day to do that, half a day. It's not a waste of time. It helps you get a sense of how it's all configured. So as we go back here now, the solvent now has cleaned out the mixing chip, and now we're advancing that band up to the top of the coil, and pretty soon our fraction collector is going to come to life, and that sample is going to be taken, the number 2 sample. So the first sample was right here on the aliquot and the vial collector. Here we go. So we collect a little bit, then into our sample into our aliquot vial, and then back to our sample, and that's it. And so now we're collecting our second sample. The rest of the band of that set of reaction conditions are now being pushed through the coil, and we're collecting all that sample. That's a total of 4 ml that we committed per reaction. Again, that can be whatever number you want, up to the volume of the collection vial, which is 20 ml, or much smaller than that if you want. It depends upon how much reagent you want to commit to that particular reaction. So now we're 45 seconds from the end. We're still collecting our product over here in the collection vial. You can see it right here is the 4 ml that we've committed to this reaction. And now it should stop relatively soon, and you'll see this line change from collecting product to wash. So 15 seconds left, And you can see this is the end of the dispersion plug. So this is the 4 ml have already come through. That's our hard cut, but this is still not quite clean here yet, and the wash will take care of that. You also have all the solvent behind the bottom of the coil as well. It is completed. We're rinsing this out, and the system is equilibrating and getting ready to run the third reaction, which is again is a higher temperature. So anyway, I've taken you through, two sets of reaction conditions with the automatic system. I've shown how it could go to do 10 reactions at the same time. Again, in this particular instance, it's a residence time, the volume of reagents, and the temperature can be pre-programmed in for all 10. There's many more degrees of freedom with this system, meaning that there could be additional coils like this put in sequence with other systems that are connected, that are slave to this robot. Plus there's also, I haven't shown you, software for data acquisition to look at a spreadsheet in terms of exactly what you did and line that up with your experimentation. And also additional units that are on the Uniqsis website for photochemistry, low temperature cryogenic reactions, and also for flow UV. Let's just mention the photochemistry one. It is the most powerful UV lamp that is out there, 700 watts, can be configured in different nanometer LEDs from 360 nanometers up to 560, and in any combination that you want. You'll have to talk to us about that to find out more about it. But in essence, what we wanted to do here is just show you the basic configuration, if you will, and how that operates. And we hopefully this has been educational for you, and we look forward to hearing from you. Thank you very much. Well, that concludes our demonstration for today. I hope this has answered your questions about the Uniqsis flow chemistry system. My name is Peter Joyce of Sentinel Process Systems. You can reach me at the email and phone number below. And remember that Sentinel is the authorized and exclusive distributor for Uniqsis products in North America. Thank you, and have a great day.